right? And I mean, obviously they're not arranged, well ordered like that, but.
When the slope is 0, it's like the perfect amount that you want. It's a sweet spot.
I don't know. I mean, if you're trying to maximize rate, sure. That's not always what you're doing, but that does give you the maximum rate. Yeah.
So how would C affect things if we were like considering it, or would it just get too complicated?
It wouldn't get too complicated. It just now again, if you're holding the pressure of B and C constant, it just shows up as another little thing here, right? Some of these B's will be C's, but you're not going to notice. If you're varying both of those things at once, there are things where they're product inhibited, right? You make something, but it sticks to the surface and it slows you down. And so you just get a different curve. And so like another thing that you can do is you can, this can, for example, a lot of times what you'll see in literature is this is, instead of holding B constant, this is at 1 pressure of B, and then you'll see another curve at another pressure of B. And so it depends on where you are, but if I increase B, that might decrease the rate. So a lot of times you'll see curves like that. And so you need to be able to look at this and say, okay, in this pressure range of B, B is inhibiting the reaction, right? Over here, A is speeding up the reaction. Over here, A is inhibiting the reaction. So all these things can be happening. And then C is just another term. So you could draw another curve for changing the pressure of C. The only difference between C is it can only inhibit, right? If our mechanism is correct, then you're never going to have a regime where C increases the rate. It's only going to inhibit the rate. So let's try to look at an example. Now that has chemistry involved. I don't want to do this one. We're going to do one from my research. I don't need notes for this. It's a longer mechanism and stuff, but I think we can simplify it enough that we can talk about it. But at least there's some interesting results in it. Okay, so I'm going to start by telling you the observed rate equation. Because this is what I'm given often when somebody pulls me into a project. They've already done kinetic data, and they want me to tell them what's happening. So what they did is they held the pressure of hydrogen constant. I should tell you the overall reaction. C2H6 plus hydrogen makes 2 methane molecules. So this is ethane plus hydrogen makes methane. I'm adding hydrogen to methane, to ethane, right? And I'm making methane. All right, and I vary the pressure of ethane. And the rate that I get looks like this. I don't know how many data points they gave me. It is perfectly straight. Okay? And now I'm actually going to change this a little bit. This will log scale, this will log scale. And now I'm going to vary the hydrogen pressure. I'm going to hold ethane constant. And here's my rate, and you get something that looks like this. So increasing the pressure of hydrogen, which is a reagent, decreases the rate of the reaction. And the slope of this curve is -3. So, what's my rate equation? This goes through 0, by the way.
It would be K times PCH, P ethane
Yeah, I'm going to,
over P hydrogen Q.
over hydrogen pressure of hydrogen cubed. Do I have any questions on how he got that information?
Yeah, how did you get that?
Sure. So let's say that the pressure of hydrogen is held constant, okay? Now that's this curve. So this curve tells me that the rate is essentially equal to some rate constant times what? The pressure of ethane. You're not confused there, right? You got that?
Oh, I see.
But again, this rate constant includes the pressure of hydrogen that was held constant. Does that make sense?
I get it now.
Okay. And then this is the same thing. The slope here tells you the exponents. If you think back to like power law kinetics, the slope tells you the exponents. All right, so this is what we get. So what has to happen between, I'm going to just say, I have a starting point, and let's say that we don't know what this is. We don't know, in other words, we don't know what's on the surface when we start. Remember over here we said we're going to be covered in A, and then we're going to make this, okay? So now let's say that we don't know what the starting point is, and we also don't know our transition state. Both of these things are unknown to us, but what do we know? So let's analyze the numerator. What's in the numerator? Okay, so what has to adsorb between the starting point and the transition state? What's in the denominator? So they have to desorb before we form the transition state. So again, I haven't done anything with chemistry. I haven't done anything with DFT, nothing with mechanisms. I don't even know what type of metal this is. And yet I can already tell you what has to happen between whatever my surface is covered in under these conditions to form the transition state. Yeah?
Well, wouldn't it probably look different in that case? You probably have, you can't have diatomic hydrogen bonds to this catalyst.
True.
You'd have too many valencies for the hydrogen.
Yeah,
And
you're right.
you'd also have to have ethane carbide with two sites to break that double bond. You'd have a multivalent carbon.
I haven't said anything about how many sites I'm using.
Well, you have hydrogen, it just says you have that molecule coming in as a whole that's not leaving or entering as a whole.
No, you're right about that. It doesn't leave or enter as a whole. Again, I haven't said anything about what this transition state looks like. I haven't said anything about what my starting point looks like. And yet I already know from the rate equation what has to adsorb and what has to desorb. That doesn't mean that it just adsorbs and desorbs. There's other things that are going to happen in between. This isn't like A plus B goes to C. There's 20 steps that happen. Yeah.
So what exactly are we trying to do? Are we trying to derive the real rate equation
Yeah.
to be observed?
Well, we're trying to derive the rate mechanism. We're trying to understand the mechanism.
Gotcha.
And we want to be able to go backwards too. You know, if I give you a mechanism, I want you to be able to derive a rate equation.
Right.
But I also want you to be able to look at experimentally derived data, come up with an observed rate equation, and understand something about the mechanism. Now there's only so far you can get before you need something like DFT or something really sophisticated to help you map out the pathways. This is obviously not, you know. Any other questions? All right, let's look at the mechanism. Does this seem weird to anybody else? 3 hydrogen molecules have to desorb, and ethane adsorbs? No? All right. We'll talk about some things then. So let's start with adsorption and desorption. It's probably a safe bet that hydrogen adsorbs and desorbs from the surface. But how does hydrogen adsorb and desorb from a surface? Does it do it molecularly, or does it break apart? We talked about this last time.
You can have it both ways.
So I need 2 sites, and I'm going to form 2 atomic hydrogens on the surface. We talked about this a little bit last time. Remember, this was called dissociative adsorption. Okay, what about ethane? Yeah.
Probably gonna go in 2 sites at once.
But it's not.
But how would it dissociate upon adsorption? Which bond breaks?
The double bond between the carbons.
You think the carbon-carbon bond breaks right off the start?
It's like a.
It's a single bond, first of all, but you're saying that the carbon-carbon bond breaks upon adsorption.
I don't know, I just think that ethene.
I think that's all you drew it last time. Maybe.
That's ethylene. This is ethane. They're,
Close enough.
you know,
I think it fits.
well, they're close enough until you have to worry about the bonds.
I think it
Yeah.
fits as well.
You think it fits these orders? Okay.
Yeah.
Doesn't get.
How many sides?
It's a large molecule, so it's huge.
Okay. All right, so after it physisorbs, what happens? What bond is going to break? Think about, what do I have to do in order to make methane? Say that again. You can't. Well, I mean, let's first just ask the question: what do we have to do in order to make methane? We have to break the carbon-carbon bond. So let's just write that down. I'm going to get tired of drawing all these arrows as reversible. So. Anybody have a problem with that? That's what it makes, right? Those are both methyl fragments on the surface. They each take up one site. So that kind of supports the idea that we said ethane might take up 2 sites. It's roughly twice as big, right? What else might it do? Instead of that, what else could it do? If it's ethane,